Hello and welcome back to the channel. My name is Mons, and today I'm going to show you how to use the simplest machine learning tool there is, linear regression. So by the end of this tutorial, you will have learned how linear regression works and the steps to downloading, analyzing, and predicting data with linear regression. And third, how to interpret the evaluation metrics R-squared and mean absolute error and the coefficient of the model. So to teach you this, I've set up a scenario where you're a data analyst in a real estate startup. And your job is to help the team estimate house prices based on the size of the apartment. So, and the tools you get to do this is access to the historical data of the apartment size and their final price. So, generally the steps that you want to take when doing a task such as this is to first get the data set, visualize the data, and then fit a linear regression model onto this data. And then you want to predict unseen data that the model hasn't seen yet, and you want to evaluate the model. So, the first step that we're going to do is explain what linear regression actually is. So, linear regression is a tool for predicting an unknown variable or the dependent variable given independent variables. So in this scenario, we will have the area of the house, which will be the independent variable, and the price of the house, which is the dependent variable. So we're going to try to predict the price given the area. So let's say that these points correspond to house prices on the y-axis and the area on the left, on the x-axis. So what linear regression does is that it tries to put a straight line in the optimal position where the error in the y-axis is as small as possible. And it's not only just the y error in the y-axis that matters, but it's the squared y error. So a bigger error is punished more than a smaller one. So the bigger the error, the distance becomes, it's squared. So the line wants to avoid big errors as much as possible. So what it does is that if we shuffle the data here, we see that we have lots of bias. Okay, let's do this one. Great. And what it just tries to do iteratively is to find the best bias and the best weight for this line. So this is basically the intercept, raising it up and down. It's trying to find the best point, and then it adjusts this for a little while, and then it tries to adjust this too. Then it tries to go down, maybe down a little bit. We can go up here. This is a pretty good one. See, the total area of these errors is now pretty low. So we can see the mean squared error here is 4.7. So if we go down, we have 4.77. This is the lowest. And if we go up, 5.1. So this is kind of the lowest error that we can get. So this is how linear regression actually works. So let's get back and actually try to download the data, which we will do via Kaggle. So getting the dataset from Kaggle. So Kaggle is a website where you can download datasets for analyses. So we're gonna go onto Kaggle, and this page is already loaded, and this has housing prices. So if we go down and look at this CSV file, we see that there are lots of different houses, and they have details about price, the area, the number of bedrooms, bathrooms, stories, lots of other data. And what we're going to do in this video is we're going to try to predict price only based on the area of the house. So let's go ahead and download this as a zip. And we can just drag it into the same folder as we have our working notebook. So here we have the dataset, and we see that just as in the website, we have the columns for price, area, bedrooms, apartments, bathrooms, stories. And what we can do now is we can import this dataset. So we're going to create a data frame and load it with pandas, which is a tool for basically working with Excel sheets kind of data. So we use read CSV and then the file name, so housing.csv. And then we're going to get only the relevant columns of this dataset. So the first one is the sizes, and that's going to be equal to data frame of let's see what the name is, area, and prices will be equal to the data frame of price, I believe it's called prices. And now we're gonna create a data frame with the adjusted units, which basically just means that we do this data frame. Then we do with adjusted units, it's basically I'm doing this with a dictionary, and we're doing this with the data frames that we just created. So the column for size, I want them in square meters, will come from these sizes, and the price in dollars, which is the unit, will come from prices. And now we just close this bracket. Great. And just to have a look at the data which we have right now, we can do dataframe.head, and we see that if we run this data frame, there we go, run this, and now we have the size, square meters, and price in dollars. So the price was already in dollars, but I noticed that this is not square meters, this is square feet. So I happen to know that the 1 square meter is I happen to know that 1 square foot is equal to 0.09 square meters, 93. So if we run this again, now we see more accurate sizes. These are big houses. And what we're now going to do before we get to training is that we're going to divide the data into 2 different sets. So we're going to have one set for training the model, actually fitting this line, and one other which the model won't see. And then we will use the same model on the unseen data. And the reason why we do this is that we want to have an idea of how well this model will perform on data in the future. So let's say this real estate startup has a new listing, and it wants to try to predict the price of this apartment, or likely house, and it wants to predict the price of this apartment. Then we want to make sure that we run this simulation on unseen data, and that will give us a rough estimate on how well our model will actually perform. So the way we do this is that we define variables for xtrain and xtest, ytrain, and ytest. And that is equal to the train test split of the variables that we have. So that would be data frame of size M2, and also the data frame of the price in dollars. And we also do the test size equal to 0.2, 0.3 is normal, and this just had the wrong name for the column. And once we've done that, now we can visualize the data. So what we want to do now is to make a scatter plot. plt.scatter with data frame of the size M2. And on the y-axis, we want to use the data frame of the price in dollars. If we have a look at this, now we see the size plotted against the price in millions. Okay, this is not millions actually, it's just dollars. We have the units over here, so this is to the power of 7. So 20 million, 40 million, no, 2 million, 4 million, $6 million. There we go. Okay, great. And we see that there definitely is a trend. It's not perfect, definitely not pretty far off, but we do see that the bigger the house gets, the more expensive it generally is. So now let's actually fit the linear regression model. So what we're going to do first is we're going to initiate the model, and this is done by making a variable called model and then just calling linear regression. And now when we fit the model on the training data, we use model.fit, and we use the x train, and we fit the x train variables to the y train. Great. We try to run this. Great. That's trained. And now we're going to try to run this model on the x test, so the data that the model has not seen before. So we're going to run model.predict. We're going to store it in ypred. So this is the predicted price equals model.predict x test. Perfect. I'm going to predict this. Perfect. And now we can visualize the model by running this little code. And this is prepared just to be able to see the data and the line which it has run the data on. So this is the line that results in the least error, the least mean squared error on the entire training set. So let's go ahead and evaluate this model. So the two metrics that I will teach you how to use is mean absolute error, and we will use the pre-built one for that. We can compare y-test to ypred. So this will calculate the difference between these two. We will also look at R2 and R2 score of the same y-test and ypred. So we're comparing the actual price to the prediction of the model's price. The prediction of the model of the price. And now we'll print our metrics. And another important metric of the linear regression model is the slope. So how much it increases in y for each unit in x. So well, let's have a look at it. And coefficient. This is the slope. And this will be model dot coefficient 0. This is just for getting the slope. And here we have, I want to have 2 points of decimal, 2 decimal points. We will also want to print the mean absolute error. Mean absolute error equals to MAE. And we also want to print the R2 equals to R2. All right, let's have a look. So our coefficient slope is 4,835, and our mean absolute error is 1,186,328, and our R2 value is 0.27. So the coefficient, or the slope, means how much it climbs, this line climbs in y for every step in x. So when we increase the size from 200 to 201, what happens to this prediction? It increases with $4,335. So the interpretation is, if the coefficient is 4,800, is that on average, for each increase in square meter, the price will go up by $4,835. That's the interpretation. The interpretation of the mean absolute error is that on average, the model has an error of 1,186,000. That's quite a lot. It's not a very good model. And the R2 is basically how well this line is fitted to the data, and we'll get to that in a second. So, mean absolute error. So what does mean absolute error mean? It basically just takes the predictions of all of these. These are the test set, and the red ones are the predictions that the model has predicted. So you see they basically turn into a straight line. And what mean absolute error shows is basically on average how long this line is. So this line is very long, and it just adds all of these up and divides them by the amount of points. And in this case, we come up to the number of roughly north of 1 million, which makes sense, which is basically this distance, which seems to be fair. And the R2 value, which is the coefficient of determination. So what the R2 value, which is 0.27, it basically measures how well the model explains the variation in the target variable. So right now, 27% of the price seems to be determined by the area of the house, because it can explain 27% of the variation. So if we had a 1, then it would explain 100%. Then it means that as soon as you increase the area of a house, its prices go up by a fixed amount. Rarely this is the case, but the higher this number, the more the dependent variable is determined by the independent variable. And if it's 0, then it's the same as just predicting the mean of the y-axis, of the y variable. And the mean absolute error, that measures, as I mentioned, the average absolute difference between predicted and actual values. And it's in the same unit as the target variable. So in this case, roughly $1 million. And the interpretation is that we want to have as low as mean absolute error as possible, because that means a better performance of the model. And it's also a very good metric because it's very easy to understand. Like, on average, how far off are we? And that's how you use linear regression for regression tasks, and how you download data from Kaggle, and how you interpret the values. I hope you enjoyed this video, and I'll see you in the next one.